In this one, we will try to investigate or try to find out the equivalent model or means electrical circuit model for three-phase induction motor. Now, what is the issue here is that before I start, obviously we would like to develop it based on its analogy with transformer, but at the same time, as I have mentioned in my last video first part, that needless of means there is no need that your stator and rotor winding must be wound for same number of phases. We can have phases for stator and rotor winding. However, both of them must be wound for bound for same number of poles. So what does that mean? That now why I am putting emphasis on this, like try to understand that why this different phase is problematic, because if it is a different phase, then what you will get here is that it is something, how can you go for a per phase analysis? Here the question, like for any balance system like we did for three-phase synchronous machine, we go for a balanced analysis. But if the rotor and stator are not of equal phases, then how can we go for a balanced per phase analysis? Question or means matter of concern here is that getting a per phase circuit. Now, if you are stuck, then let me help you by giving you the analogy of a balanced balanced Scott connection. So, if you go back to that balanced Scott connection, for each three side of the primary winding, actually rather it was two primary winding was there, but if you consider that each of the phase same amount of current was drawn from each of the phase, and thereby it could be visualized like if you consider only the primary side. Try to understand here, we can only get unlike transformer, in case of induction motor we can only get equivalent circuit model from stator side, because rotor side is mechanical. So mechanical side we cannot access. Only from stator side we can get an electrical analogous viewpoint. So if that electrical analogous viewpoint we want to explore, then we will find that in case of that Scott connection, it was also same. There was no big deal. When it was balanced, you can represent it as a balanced, means in that case all the transformers were, means all the, not transformer, rather all the phase were delivering same amount of current and thereby the same amount of power to the primary side. And here also, so in case of balanced operation, instead of analyzing all the three phases, analyzing one phase was sufficient. You agree with that? Now if you agree with that, now come here, and even in case if you have different number of phases in your stator and rotor, but if you are having a constant same number of poles is required, means both stator and rotor are acting on same core. It was not like, in case if you think about having a transformer, it's like this. A Scott connection, say here it is your primary side, let our high voltage side is primary side ACB, and here you have, it's like this. You take another transformer, like this is one transformer you are having, but instead of, means you are having actually two transformer. One is having this teaser, you take the teaser winding secondary, and instead of connecting means secondary of the main transformer, what you did, you take another transformer, you take and connect its primary with a large inductance with the secondary of the teaser, and then you try to feed it. Like here what you are doing, you are only loading, and here you are having your this is your, say this is our N, so this is AN point, this is a large inductor L, and here you are having another auxiliary transformer. While you kept your this side unused. Now if your this L is sufficiently large, you can means for light load you can always get almost 90-degree phase displacement between these two windings. Whatever voltages or current you will get, this will be means there will be a means phase shift. Now, but problem is that if you do not connect a load with this, rather you connect same amount of resistance across this and this, you are going to create an unbalanced situation. There will be a heavy current will flow through this A and also B, C, that phasor will not remain balanced and you cannot go for per phase circuit. The purpose of showing you all these things is to make you understand that why this one is necessary. Both of them must be found for same number of poles. Same number of poles means here in case of transformer, all this, whether you are doing 3 phase to 6 phase, 3 phase to 2 phase, 3 phase to 12 phase, the primary and secondary should act on same number of magnetic circuit. And if you differ the magnetic number of poles, there will be mismatch in your magnetic circuit. Try to understand this or rather realize this very point, this subtle concept, that it is not the number of phase that difference in the number of primary and secondary phase that matters. What matters is that the um, matching of magnetic circuit, because that is the medium through which you are converting. So if that conversion medium is not matching, then there will be a problem. Otherwise, everything is okay. Like suppose now you are in India and you want to go to USA. So in currency exchange mechanism, you say convert your 1 lakh rupee in corresponding USA dollar. Now, if while this exchange takes place, now if somebody, some means hacker or someone like who is doing this kind of online fraud, he hacks the system and takes out 50,000 of your rupee during this currency exchange, and you got something else there. So that is problematic. It is not required that when you are having, if you are having 1 lakh in Indian currency, the same amount of 1 lakh you will get in American currency. It's not required. You are also okay with that. But once, and if that 1 lakh and American currency, these two are proportional, as long as when these two will be proportional, as long as your conversion mechanism remains intact. But in this conversion mechanism gets affected or altered, then whatever you will get, there will be no parity between your Indian side money and USA dollar. And another problem is that if the conversion mechanism remains intact, then for if for 1 lakh you get a proportional amount of USA money, then you can figure out, okay, for 1 lakh we are getting this, so for 100 rupee how much it would be in USA dollar or USA currency. But if that means inside that there is a means hacker or some means spammer takes control and alter this conversion process, then there will be no parity between what you get in USA side and what you have in your Indian side. Even if they may do some manipulation, so you may have a situation where both sides are having same amount of money, numeric value in both currency are equal, but that also will be a problematic situation because you do not know what is happening inside. So that conversion mechanism should be intact, and that is why the number of poles of stator and rotor winding must be same, otherwise there will be a huge problem. I hope this example gives you some insight about that problem, what which you may face if you have mistakenly wound your rotor with different number of pole structure. Now, following the same analogy of this conversion, you can also do that. Suppose after converting in USA, you spend something in USA dollar, then also you can figure out that what would be its corresponding, means your expenditure's corresponding value in your Indian currency, as long as your this conversion is intact. So with this understanding, let us try to develop a model, and thereafter the like the means equivalent circuit for our three-phase induction machine. Now for this three-phase induction machine, so one thing it's clear that we can consider it analogous to transformer, and if it is analogous to transformer, then we will try to consider transformer model to develop it. And like three-phase transformer can be in balanced condition, can be represented by a single phase equivalent one, we will try to draw this kind of situation here. So let us write a few things that will be used in our analysis. P, we know number of poles. Then we are having F, that is supply frequency. In our India it is 50 hertz. Then we are having FR, sorry, F2, that rotor sometimes we can say this is Fs also. Now we are having now we are having our rotor speed, and then we are having and your phi or phi m is the amount of mutual flux. Now what we can write, and also here regarding rotor winding, one thing I would like to mention that generally during runtime we will show, and also you can understand that when the rotor speed is sufficiently high, that means uh, NR is close to NS, then sleep is small. And for the small value of sleep, uh, what we will see that our this one, the rotor induced EMF and also current, their frequency is very small. And also one thing we will be able to show you, just let me write the formula, then you will get it. Like E1 is equal to that our famous and very own equation, it is KW1 if N1 5 volt and E2 is equal to 4.44 kW2 SF. Now see here E2's magnitude is SF. So if this E2's magnitude is SF, then it is obvious that when S is small, you are having a small value of E2. And if we are talking about this fundamental is having a small magnitude, then you can understand or intuitively anticipate, your intuition can help you to anticipate that the other higher order harmonics value will be smaller than that of the fundamental. So here we don't need to do much engineering with our rotor structure. Means harmonics can take place, but obviously harmonics frequency will also be small, because S will show that in most of the cases S lies within, for most of the ergonomically designed motor, S normally lies between 0 to 0.3 to 4. So for the small value of S, you can understand, say if your supply frequency is 50 Hz, then here the fundamental will become say 15 to 20 Hz. And obviously even if the higher order harmonics are having frequency integral multiple of your fundamental, but if the fundamental itself is 15 Hz, then 5 times of that will be 75 Hz. But here 5 times of this one, fifth harmonic for stator will have a frequency value is equal to 250 Hz, while this one is having 75 Hz. So means the chance of the rotor harmonics to interacting with the outside surface also getting reduced. And also there is something like that it is inside your stator shield, so the stator structure will also provide a shielding. So there is a, but means little chance that it can interact with your outside harmonics. Only thing that is means problematic is that sometimes it causes undesirable mechanical problem, like it started means induction motor starts kind of cogging and crawling. Those I will discuss, but for and means sometimes it causes problem in terms of because during start your sleep is 1, and at that time rotor frequency is comparable with your stator frequency and cannot be means neglected. or so in order to avoid that means undesirable effects due to rotor frequency, sometimes what we do that we skew the rotor slots just to avoid that kind of means unnecessary interlocking, that is known as fogging. We will discuss later, but uh, first means here my purpose of discussing this is that you don't need to be very cautious about selecting KW2. The effort required to select KW1 is very important, but not KW2. Rather, skewing of rotor bars can always help you to a great extent. Well, so this is quite like a transformer primary secondary equation. Only thing is here is that you are having something that is proportional to your slip. So what we can do is that instead of writing it E2, if we consider that E2 is standstill induced EMF, we can write it like SE2. So SE2, because this E2, then E2, if we define E2, standstill rotor induced EMF, then we'll get this. Now let me draw the transformer circuit, transformer equivalent circuit. Okay. This is your secondary side, and due to the presence of end ring, this the rotor bars are shorted by end ring, so you can see consider that it represent the rotors is represent a short circuited secondary. So this is R2, this is JX2, this is SE2. Now here one thing, there is one twist, that being a frequency dependent factor, instead of x2 you will have JSX2 here, and here you are having E1. This is your rotor supply side voltage you are giving. This is I1, this is I0, this is I2, sorry, this is I2. Well, now like if we instead of taking the electrical things, let us first try to understand in terms of MMF balance. So in terms of MMF balance, what we can write, think about it in terms of MMF balance, because in case of transformer you need to introduce that MMF balance first. So what is your primary side MMF? Primary side MMF A1 is equal to if primary side phasor phase number of phase stator is equal to let this be represented like N1 dash I1 and A2 is equal to right. So that in terms of MMF balance, what we can write the equation which was common for transformer, that is correct, and thereby it gives, sorry, oh god, it gives I1 is equal to I naught minus N2 dash by N1 dash uh, I2. So in terms of your your phasor, we can draw it like if we know the secondary side. Let us assume that somehow we get the short circuited secondary winding power factor some value, say this side is E2. I'm trying to copy it from that transformer diagram. E1, then the secondary current is like this is theta 2. So you are having a reflection of that. Now your I naught must lead this by an angle of 90 degree. So this is your I naught, this is your minus N2 dash N1 dash I2. So once you have this, you add them to figure out your this is your I1, this side is your minus E1. But hold on a second, think, think well, that what is the frequency of this E2? The frequency of this E2 is SF, I2 is also SF, however E1 frequency is F, I1 frequency is F, I naught frequency is also F. So it is it is like we are doing some logical mistake, because we cannot plot two different frequency waveform in a single phasor, isn't it? Try to understand. During run, the way we have defined sleep is less than 1. In motoring mode, sleep is in this value. And once sleep is less than 1, then the frequency of your rotor and stator rotor induced EMF and current flowing through it are not same as the stator current uh, flowing through the stator winding or stator induced EMF, isn't it? So what is the mistake we have made here? Is this incorrect, or we have made a subtle things that what we means just we just means forgot to consider here is that your rotor, what I said in the last part of my previous video, your rotor induced EMF is getting induced with respect to a frame that is not stand still. Your rotor structure, when you are considering S less than 1, then it implies your rotor structure is rotating at subsynchronous speed, but its speed is not 0. Rotor structure speed is 0 only when S is equal to 1. Otherwise, rotor is having some value. And what is the rotor's mechanical speed of rotation? It is Fr, and that is equal to 1 minus Sf. And this Sf or F2 is equal to Sf. We measure this F2 with respect to this Fr. So with respect to a standstill frame, it will be F2 plus Fr is equal to 1 minus Sf plus Sf is equal to F. So both of them, while we are drawing the phasor, we are drawing it with respect to a stationary frame. So both of them are having same frequency with respect to a stationary frame, and that is what allows us to draw the phasor diagram in a single diagram. So once you understand this, then it is not difficult for you to draw the phasor diagram, as the secondary side is short circuited. So what you can do is that you can write that E2, or rather SE2 is equal to I2 R2 plus J SX2, right? So this gives you what? This gives you something that is well. Now one thing that is interesting, one small manipulation we can do is that we can divide both sides of this equation by S. And I have already discussed in my last video that for motoring, S is always not is equal to 0. S cannot be 0. That means an induction motor cannot reach synchronous speed, because once it reaches synchronous speed, the rotor current will become 0, and thereby the torque production, reason behind the torque production or derivatives of the torque production will become non-existent, and due to that there will be no torque to overcome the mechanical retarding force continuously acting on your rotor mechanical part, and thereby the rotor will start or will undergo a kind of decelerating stage or will decelerate, and as soon as it starts decelerate or slow down, you will find that rotor slip again become something greater than 0. Therefore, s is equal to 0 is not a valid option. S is always not is equal to 0. Therefore, both side can be divided. We can divide both side by s. Fine. If we divide both side by s, what advantage it will give us? In terms of phasor diagram, we can draw this like this side will be I2 R2 by S, this N2 and this side will be like your this, let it be I2 dash x2 j I2 dash x2, and that gives E2 dash, while E2 dash is equal to what? E2 dash is equal to into by N1 E2. So this E2 dash is equal to also E1. I just need to draw it in scale, so it will give you E2 dash, sorry, this E2 dash is equal to E1, and therefore that minus E1 now we can find out I1 and what is V1? V1 is equal to I1 R1 plus JX1 minus E1. So draw I1 R1, then draw I1 JX1, then join it to figure out your V1. So this is our V1. What is the input power factor angle? This is our theta 1. This is input power factor angle. This is output power factor angle. So clearly a few things we can observe, that output power factor angle is clearly a function of rotor speed or slip, and needless to say that when you want like if you think about it, it is like we have already know the analysis. If we put an electrical load across our transformer secondary, how the primary side sense that a load is or a load change is takes there is a load change in the secondary side. That analysis we know that secondary side current produces or secondary side change in current produces a change in demagnetizing MMF, and by sensing it, transformer primary side also change the input current to counterbalance that change in demagnetizing MMF produced by secondary side current. However, here the secondary side is short circuited, but it is a part of it is a function of rotor speed. So what would happen if you put extra load on the rotor shaft, then how this will so I was talking about how this your load will be means when you put some mechanical load on your motor shaft, that your stator side will sense that there is a load is you put a load, a heavy load or something, you connect or couple a generator, or even if the generator was previously coupled with your motor shaft, now you connect some electrical load with the generator output terminal. That means you are putting more load on the generator terminal, and thereby generator will produce counter torque, and that is going to reduce the speed of the motor. So how the stator current means stator will sense it and counterbalance it? That is the twofold questions. Now here, first of all, how stator will sense it? Once you add additional load on your motor shaft, say previously your motor was producing some torque, say T. In steady state condition, the torque produced, say T, let me use a different color to make you understand. Say this was TSS, that is the steady state torque, and that was sufficient to counterbalance your means mechanical torque generated due to retarding forces. Let us write it as retarding torque. This is the condition in steady state. Now once you put more load on the rotor shaft, that additional load, then what would happen? Due to this additional load, this TSS will become less than the sum of these two. Now due to this, your motor will start a decelerating motion, and therefore once you means this can be we can write it like adding of additional load on the motor shaft is like increase in S. Now once you increase S, what would happen? Let us see here what is happening here. If you change S, then that will change the relative speed. If we change S, then the relative speed of this magnetic flux will increase, and thereby it will increase F2. And once F2 is changed, then what would happen? For this different value or increased value of F2, you will have here more value of SE2. So this higher value of SE2, like more means SE2 will become higher than its previous value, because all other factors remain constant. If we look at the equation of SE2, we will be able to understand it more clearly. The equation of SE2, somewhere here I have written it. Yeah, so you can see that this flux phi, I have already mentioned that leakage across our primary winding never exceeds 8% of its even in full load current. When the full load current is flowing, then also the primary leakage never exceeds 8%. So we can consider our mutual flux remain more or less constant, and with that assumption we can say that this E2 is a function of S only. Now if E2 is a function of S only, so you are basically going to apply a higher voltage across a circuit with fixed elements. Now if that is the case, then what, or not fixed element, even you are applying this. Well, one thing you may ask me that if we increase S, then it will also change the value of Sx2 also. So what kind of change we can expect? Like if we try to write the expression of I2 is something like, so it is clear that if we simplify, it will become, so from this equation it becomes clear that if you change s, means if you make s, if you increase s, then I2 will also increase. So from this we can say that there will be a change in I2, because s is appearing in the denominator term. This will, if you increase the value of s, that is going to reduce the value of this R2 by s term, and uh, like that will uh, means give you a considerable increase in I2. Now once you are having a change, means load, change in load on a motor shaft is going to change your I2, and once you sense the change in I2, the remaining part is just like a transformer uh, change in secondary side load, because we just need to establish a connection between secondary side current and mechanical load. So once we establish this, they are not, the remaining part is just like a transformer. More I2 means more demagnetizing effect produced by our secondary current, and therefore the primary will draw more current to counterbalance it, and thereby the primary will absorb more power from the source. So if I need to draw the equivalent circuit, what we can draw the equivalent circuit? The equivalent circuit will be something like this. Again, I will give you more topic to, means more issue to, means you will find problematic, and will get, means you'll find it pretty confusing, but actually they are not. But you people love to dwell between books, and that dwelling between books, I do not know how that helps you, but that is the choice you made always. Anyway, okay, now see what we can write here is that, just a minute. So that if you follow physical or other books, you may find that they are taking it here, this branch, like we did for transformer approximate equivalent circuit. If you follow Chapman, that is a popular book also, you will see that he is giving you argument that this branch, unlike transformer, cannot be shifted here, because the no load current for induction machine is concentrated, means if you consider percentage wise, like no load current of a transformer and with its full load current, and no load current of an induction motor with its full load current, you will find that no load current of an induction motor is at least 20 to 30% of its full load value. So by that argument, while in case of transformer it is hardly 5 to 10%, and thereby in case of transformer the drop across this primary side series branch is very small, and thereby we can bring that magnetizing branch ahead of our series branch in case of a transformer, while in case of an induction motor it is difficult to bring it in front of the series branch. However, if you observed, or means if you were mindful while watching this video, you must have noticed that I have mentioned about constant your constant uh, mutual flux. So by saying constant, that means I am assuming that I have already brought it in a place where the series branch current cannot make any change. So basically, by the argument which I have developed this circuit diagram is like it is this branch is not here, rather it is located here. Although I have presented an argument that even if branch is located here, then the induced means the flux that is going means this branch is going to get will no way, and variation of this flux if you consider with this branch is uh, from 2% to 8% for different loading of induction machine, and therefore it is fairly means there will be no such kind of means uh, what to say, that it will not be very, it will not introduce any huge mistake in terms of, or error in terms of correction means correctness or accuracy of the model. So this means if you do not want to bring it in front of the series branch, you will have your argument. If you want to bring it in front of the series branch, you in that case also you will have your argument. So there is no such conflict. You must be respectful to others' view, what Chapman says and what your Bhimra and other Indian author says. Both are not means it is you are people are like two argument, like two fighters of some professional wrestling match. One must beat other, or means other means you need a knockout, otherwise it can be possible. And but in science it is like there are subtle difference between the two concepts, and maybe both of them are leading to the same conclusion, but just having a different, slightest different in perception, leading us to different equivalent circuit model. So there is no need to be worried, or means be afraid of that. In addition to this, what one extra change what we can do is that for normal motoring mode, as I have said, it is S is 0 to 1, we can break this R2 dash by S, like R2 dash, that is the physical rotor resistance, plus R2 dash by 1 minus S by S. This is a virtual resistance present in your system that represent our means this one. This one is representing fictitious resistance that is proportional to your mechanical load, and mechanical power, converted mechanical power, will be something that will be 3 I2 dash square R2 dash 1 minus S by S. This is the amount of power that is going to be received or means that is the amount of converted mechanical power. Once you discard the losses from this, you will get the available power across your motor shaft. Means what is the mechanical power that you can extract from your motor shaft, you can get it from this equation. Now one interesting things here is that uh, we can go for our in next I will discuss our uh, approximate equivalent circuit. Then also we will discuss power flow equation and torque speed characteristics in my next video, and in next to next we will discuss circle diagram of an induction machine. That circle diagram will help us to visualize how a machine can transit from motoring mode to generating mode. Okay, so with that I am going to conclude this video.